Hello, and welcome to our discussion of the path independence theorem. This theorem will characterize when a function can have an antiderivative, at least when the function is defined on a domain in the complex plane. So we begin with a subset D of the complex plane that's a domain, and we take a function f on D that is continuous. Then the following are equivalent. First, f has an antiderivative on D, which is to say, there is a holomorphic function big F defined on D such that big F prime of z equals f of z for all z in D. Second, if gamma is a closed curve whose image lies in D, then the integral over gamma of f is equal to 0. And third, the so-called independence of path part, if gamma 1 and gamma 2 are paths in D with the same initial and terminal points, then the integral of f over gamma 1 equals the integral of f over gamma 2. So it doesn't matter what path you integrate over as long as the paths have the same initial and terminal points. And of course, by the following are equivalent, I mean 1 implies 2, and 2 implies 3, and 3 implies 1. And that is the order in which we are going to prove all of these implications. So let's begin by proving 1 implies 2. We assume that f has the antiderivative big F on the domain D, and we let gamma be a closed curve in D. We want to show that the integral over gamma of little f is equal to 0. So let z0 be the initial point of gamma, and let z1 be its terminal point. And since gamma is closed, this means that z0 and z1 are really the same point, z0 equals z1. The fundamental theorem of calculus for line integrals then tells us that the integral over gamma of little f is, by assumption, the integral over gamma of big F prime, and then the fundamental theorem kicks in. This is big F of z1 minus big F of z0. But since the curve is closed and z0 equals z1, this is big F of z0 minus big F of z0, which is 0. Now we'll prove 2 implies 3. Suppose that gamma 1 and gamma 2 are paths in D that have the same initial and terminal points. And we want to show that the integral over gamma 1 of f is equal to the integral over gamma 2 of f. So we'll start drawing. Here's our point z0. Here's a point z1. Here's a curve gamma 1 that goes from z0 to z1. And here is another curve, gamma 2, that goes from z0 to z1. So gamma 1 and gamma 2 both have the same initial point, z0, and the same terminal point, z1. And we're assuming part 2, so we're assuming that f integrates to 0 over closed curves. How can we build that into our work here? Well, if we look at the picture, we've basically drawn a closed curve, if we label things in the right way. Namely, say we start at z0 and follow gamma 1 all the way over to z1, and then we'll go back to z0 along gamma 2 reverse. Then the composition, gamma 1 composed with gamma 2 reverse, is a closed curve, and so by hypothesis, the integral over gamma 1 composed with gamma 2 reverse of f is equal to 0. Now let's do some integral algebra. The integral over gamma 1 composed with gamma 2 reverse of f is the integral over gamma 1 of f plus the integral over gamma 2 reverse of f. And that's the integral over gamma 1 of f minus the integral over gamma 2 of f. And so the integral over gamma 1 of f minus the integral over gamma 2 of f is equal to 0 by the previous slide. And that means the integral over gamma 1 of f is equal to the integral over gamma 2 of f as desired. Now we'll prove 3 implies 1. So we assume part 3, what we just proved. We suppose that whenever gamma 1 and gamma 2 are curves in D that have the same initial and terminal points, the integral over gamma 1 of f is equal to the integral over gamma 2 of f. And we want to cook up an antiderivative of f. Well, here our prior intuition about what the antiderivative of f could or should be is going to work out. we'll fix a point z star in D, and we'll let z be another arbitrary point of D. We're going to try to define the antiderivative of f at this point z. Now D is path connected, so that means there's a curve gamma z in D, whose initial point is z star, and whose terminal point is z. That's just the definition of path connectedness. So let's define big F of z to be the integral over gamma z of f. First, this integral is defined because the entire image of gamma z lies in D. That's the whole point of path connectedness. Next, f is well defined in the sense that it doesn't matter what curve gamma z you pick. Namely, phi z could be another curve in D with initial point z star and terminal point z, but then independence of path, which we're assuming from part 3, tells us that the integral over gamma z of f is equal to the integral over phi z of f. In other words, there is no ambiguity in defining f by saying let gamma z just be some curve that starts at z star and that ends at z. Now here's what we need to show, that for any z, we have big F prime of z equals f of z, which, going to the definition of the derivative, means we need to show the limit as h goes to 0 of big F of z plus h minus big F of z divided by h is equal to little f of z. So what is big F of z plus h? Well, it's the integral over what I'll call gamma z plus h of f, where gamma z plus h is any path from z star to z plus h. Now, since D is a domain, D is an open set. And it turns out that because D is open, we can choose h small enough such that the line segment from z to z plus h is totally contained in D. We'll see this in a picture in a moment. Now let gamma z, as usual, be a curve from z star to z. Here's our picture. So here's our domain D. I start with my fixed point z star. I have the point z at which I'm trying to define my antiderivative. Here's my curve gamma z that goes from z star to z. And now D is open, so I can draw a little ball centered at z, and the ball, which I've drawn here in dotted lines, will stay totally in D. And then if that ball is small enough, I can go from z to z plus h and still stay in my whole domain D. And now look here, I have a curve from z star to z, that's gamma z, and now I have this line segment from z to z plus h. So let me take my curve gamma z plus h, which will go from z star to z plus h. Let me take gamma z plus h to be gamma z composed with the line segment from z to z plus h. Clearly, this curve gamma z composed with the line segment starts at z star and ends at z plus h, and the curve lies entirely in D. And for defining this antiderivative, for getting the well-definedness of the integral, it doesn't matter which path I pick, so I might as well take gamma z plus h to be this very convenient composition of two curves. So why is this convenient? Why did I go to all that trouble to define gamma z plus h as this very particular curve? Well, I did it with an eye toward my difference quotient. I want to calculate big F of z plus h minus big F of z, and that's going to be the integral over gamma z plus h of f minus the integral over gamma z. By my choice of the curve gamma z plus h, this is the integral over gamma z composed with line segment from z to z plus h minus the integral over gamma z. By properties of line integrals, this is the integral over gamma z plus the integral over the line segment z to z plus h minus the integral over gamma z. And so I've just subtracted off these two integrals over gamma z, and I'm left with the integral over the line segment z to z plus h. So we have big F prime of z equals f of z, if and only if the limit as h goes to 0 of big F of z plus h minus big F of z over h equals little f of z. And by the calculations above, I have this limit if and only if the limit as h goes to 0 of 1 over h times the integral over the line segment z to z plus h of f equals f of z. Now this may not seem to be any better. I have to show this weird limit of 1 over h times the integral over that line segment equals f of z. This limit turns out to be true as long as f is continuous. The proof is a rather technical epsilon delta argument, one of the rare times that we actually need an epsilon delta argument in this course, and I spell it out in the notes. But if you simply believe that this limit is true, then you get the desired limit of the difference quotient equaling f of z, and so big F prime of z equals little f of z as desired.